So I'd like to introduce our first speaker, Dr. Rachel Player from the Royal Holloway, University of London. I've known Rachel for many years, and when I heard the title for the meeting, Securing the 21st Century Internet, she was one of the first names that sprang to my mind. You may have heard that we're getting ready to completely rethink encryption on the internet because of the imminence of quantum computing, and there's been a big process trying to decide what the new form of public key cryptography should be. And there's been a big process where about 70 odd different designs for a new public key algorithm were submitted for evaluation. A large chunk of them, as we'll be hearing in one of the later talks today, based around the ideas of lattices. So all of a sudden we had need for a quantitative assessment of the security of a huge number of algorithms with quite complicated mathematics and range of attacks. And Rachel was spearheading the sort of costing of these and managed to sort of write the software that did that quantitative analysis of the security of these algorithms. So I'd like to say that if anything goes wrong with the internet in the next 10 years, do blame Rachel. But for that, she and other work besides, she received the 2019 Radiant Award for advancing internet security. And also as a further credential, she's also the co-author of the very short Introduction to Cryptography, which I thoroughly recommend. I was going to check Crown at Blackwell's today whether they had copies of it on sale, but she is willing to sign these if you do. But a great pleasure. She's not going to be talking about the sort of work costing lattices, but a very closely related topic that's catching a lot of attention these days in industry around homomorphic encryption. So, Rachel.
Thank you, Daniel, for the very nice introduction, and thanks to all the organisers for the invitation to speak and for putting on such a lovely event. So, having some trouble with the clicker, so I'm going to use the keyboard for now. Okay, so I'm going to talk to you today about homomorphic encryption, which is a very cool encryption technology, which I've been working a lot on. And as it's a joint LMS and IMA event, after I've introduced homomorphic encryption a little bit, I want to spend some time talking about applications of homomorphic encryption, so if you like, it's like applied maths. And then for the LMS side, I want to briefly mention some hints of like what's the mathematics I've been using or we have been using in our research that I've been involved in, that we're actually able to demonstrate like kind of what the mathematics is that we need in order to make progress in research. And I'm really pitching this talk a younger version of myself, so I came up through the number theory to cryptography pipeline, which is a familiar one. So yeah, I'm hoping at least a few people in the audience, maybe maths undergraduates who might want to see like how could the maths I'm really interested in be used in cybersecurity and cryptography specifically. And it's unlikely that I'll use the full hour. I think it's very unlikely. So please ask me many questions throughout, and I'll be happy to answer them. Okay. So first up, some introduction to homomorphic encryption. Okay, so if you've seen a talk by me before, you've seen the slide before, I apologize. Okay, so homomorphic encryption, it's a kind of encryption scheme that in addition to the usual algorithms, so key generation, encryption, decryption, it also has an evaluation algorithm. And the evaluation algorithm permits to manipulate ciphertext in the following way. So it's often explained in this outsourced computation scenario, where we've got a client in the purple and they want to interact with a cloud service. And what they particularly want to do is evaluate some function f on their data x. And they want to outsource this evaluation, have the server do it for them. However, they don't trust the server with their data in the clear. So homomorphic encryption permits them to encrypt their data x, send it over to the server, also the description of the function that they want to evaluate. And then the server can run the homomorphic evaluation algorithm, which takes as input the encryption of x and the function f, and the output is the encryption of f of x, which is transmitted back to the client. So the client's the one with the secret key, so they're able to decrypt and find the result of the computation, but the server, crucially, doesn't have access to the secret key and therefore can't learn the data x or the output f of x. So you can already start to see that if we have this homomorphic encryption scheme, this can permit us to have many possible applications, which I'll mention some of them later on. So to set homomorphic encryption in a bit of a wider context, first of all, we can think of it as in a class of technologies that are aimed to enhance privacy, so called privacy enhancing technologies or PETs. And homomorphic encryption is one example of a pet, but there's actually many, even more than is on the slide. There's just a few examples. So these technologies are all trying to give some kind of privacy to one or more of the involved parties. And these technologies differ in what specifically is being kept private, or what the privacy guarantee is, and also like how far along the technology readiness pipeline they all are. So differential privacy I'll mention because we'll hear about it in the next talk, I believe. So I won't say too much about it, but kind of roughly speaking, this is all around privacy of individuals in data sets where some statistic, for example, is evaluated on the data set. And what differential privacy is giving you is if like the data set is differed by one entry, then the output is not too different. So this basically is saying that like it doesn't matter whether one specific person is in or out of the data set, the output is not too different. So that one specific person has some sense of privacy, that their data isn't too obvious from the output, if that makes sense. So again, it's giving user privacy, but in a different sense to homomorphic encryption. Another pet that's quite similar to homomorphic encryption is called multi-party computation. Here it's two or more parties. They all want to jointly compute a function, but each of them has some private inputs. And so multi-party computation gives them a way to all learn the output of the joint function while retaining the privacy of their individual inputs. Then we have secure hardware, which gives privacy in a different way by keeping secrets in a specific part of the processor that the rest of it isn't allowed to access. And federated learning is coming up as a popular pet as well. Here we're more in the machine learning setting, and rather than like everyone's data being sent somewhere to be trained, there's more local training of data and outputs passed to some central aggregate server. So perhaps some additional privacy of user data when it's used in machine learning training. Okay, and Daniel's already hinted at it, and again, and something else that will come up in a later talk today. So homomorphic encryption, or here denoted as FHE, I'll explain the F here, fully homomorphic encryption shortly. This is kind of post-quantum for free in the following sense. So like Daniel was saying, we're moving to a future now, maybe, where large-scale quantum computers could be built soon. And so we need to think about, like, can we have cryptography that's secure against adversaries who may have classical computers, but they may also have quantum computers that can run these quantum algorithms. And that will make things like RSA or Diffie-Hellman completely broken. So we need to move to cryptography based on different assumptions. And so a lot of research in cryptography has been in this area in the last, well, at least 10 years, probably much longer in some cases. And so there's now several families of post-quantum schemes that all differ in like what the underlying hardness assumption is. So the analog of factoring in RSA is now, for example, in lattice-based cryptography, something called learning with errors, which I'll show on a subsequent slide. And so in fact, all the FHE schemes that we're using widely today and that are being considered for formal standardization are all lattice-based. So this means they inherit the post-quantum security of lattice-based schemes. At the moment, of course, it's an assumption, right? A new algorithm could come along which destroys everything, but hopefully we're not in that world. Okay. Okay, how do we actually achieve homomorphic encryption? Well, it turns out that all we need is an encryption scheme that supports two kinds of operation. So a homomorphic addition operation and a homomorphic multiplication operation. And once we have that, then we can homomorphically evaluate any arithmetic circuit. So homomorphic addition works how you expect. It takes as input two ciphertexts that encrypt X and Y, and the output of the addition operation is a ciphertext that encrypts X plus Y, where that plus is plain text addition. And similarly for the multiplication, so it takes as input encryptions of X and Y, and the output is encryption of X multiplied by Y. So this is what we need. And then I've already hinted that there's some different flavors of homomorphic encryption. Okay, so if you have one of homomorphic addition or homomorphic multiplication supported in your scheme, then what you have is partially homomorphic encryption. So that could be good in some applications, but typically to achieve fully homomorphic encryption, we're going to want both. So then on the way to fully homomorphic encryption, is somewhat homomorphic encryption. And here, this is denoting a scheme that can support additions and multiplications up to some fixed amount. So either like you can think of it as a polynomial of some fixed degree or a circuit of some fixed depth. And you basically have to choose parameters large enough, and if you do choose them that way, then you are able to get this limited amount of computation. But what we would really like is fully homomorphic encryption, and that would be a scheme that supports arbitrary computation on the encrypted data, so there's no limit, like only circuits per fixed depth. So Gentry, who already showed us how to obtain FHE, gave us this blueprint of how to build it from somewhat homomorphic encryption using a technique known as bootstrapping. And still, this is the formula we use to build FHE. Although in some applications, SHE can be sufficient, so we can use both. What is bootstrapping? So this is homomorphic evaluation of decryption. So yeah, we can homomorphically evaluate any function in principle. So what about the decryption function? Why will this be useful? Okay, so to understand why this will be useful, we need to speak about noise. One of my favorite topics, and something we'll come back to. So because of the underlying security assumption, all of the ciphertexts in FHE schemes have some inherent noise. So a freshly encrypted ciphertext has a smallish noise, and then as you do operations like addition and especially multiplication, the noise is going to grow. So you have to be aware of how large the noise is going to be at different points in your computation, because if it's ever too large, then decryption will fail. So you'll lose the functionality. So it's important to understand noise management. So if you know how big your noise is, you kind of know when to bootstrap, or you know how big to set your parameters. Yeah, so but by doing the bootstrapping, it effectively enables to reset to like an encryption of a fresh ciphertext with a smaller noise again. So you can kind of do some computation, noise gets pretty big, you bootstrap, the output ciphertext of a smaller noise again, you can continue computing. Okay, and a statement about the security of FHE schemes. So one of my favorite schemes, BFV, is also related to the BGB scheme. I'll speak about both of them in more detail later. So the security guarantee we're getting is BFV is in CPA secure if learning with errors is hard. So what do these terms mean? So if in CPA secure, you've never seen it before, it's an acronym. It's not really important what it stands for, but I'll just give you the intuition. So this in CPA security is giving you that ciphertexts look random, so that you kind of can't take a ciphertext, look at it, and know what the underlying plain text is. And so this is giving you like what you want in terms of the server not being able to know what the data of the client is, because the server just sees a ciphertext. So from that, they shouldn't be able to tell what the underlying plain text is. So that's the typical notion of security, although research is going on to refine this further. And then what's learning with errors? So this is a problem, a presumed hard problem, which can be defined in the search variant as follows. So there's some secret vector S, and then the problem is if I choose a uniformly random matrix A, multiply it by the secret, and I then add some error E, chosen from some e.g. Gaussian distribution, and I get the output vector B. And I give you this matrix A and this vector B, it's formed in this way. Your challenge is to find S. So that's the search learning with errors problem. There's also a decisional variant where I just give you an A and B, and you have to decide whether the A and B has this structure and there is a secret, or just the A and B are both uniformly random, independent of one another.
Uniformly random in which sense? So these are integer matrices?
Matrices with entry Z mod Q.
Mm-hmm. Okay.
So like.
So it's just uniformly on what?
Yeah. Thanks so much. Any other questions? And so it's this error from the learning with errors that's going to contribute to the noise in FHE schemes, and we'll see it in a bit more detail later on. Okay, so that's been a whistle-stop introduction to FHE. Now let me speak to you a little bit about some applications. So there's really many potential applications. This is certainly not an exhaustive list, and you probably can think of some others as well. But let me mention a few of them anyway. So a big application area that's of interest to many of the startups and larger companies that are working on homomorphic encryption is privacy preserving machine learning. So I've already hinted to you about like this kind of outsourced computation scenario, and one could think, I'll say some more examples maybe on the next slide, but like kind of delegating an inference could be useful. Like I might have a particular data point that I want to learn information about, but not want to reveal that. So privacy preserving machine learning can kind of directly give you a nice application sense. And we could also do homomorphic encryption to get privacy preserving training as well as privacy preserving inference, although that is harder. And so that's more proof of concept. As is the case with a lot of cryptographic primitives, we can put them together to build even bigger primitives or even protocols. So some particular protocols you could build from HE, for example, are private set intersection and private information retrieval. And we'll define this private information retrieval on an upcoming slide. We can also think about applications like electronic voting. So if we wanted to think of like having some voter privacy, we could have voters encrypt their votes, and then we could do the tallying with a homomorphic addition, for example. It's connected also to machine learning is various statistics. It might be useful to compute on data sets where you might not be able to access the data directly, but perhaps someone's willing to share that data with you in an encrypted way. And another big one that's of interest also to a lot of the startups right now is blockchain applications. So this is not something I know a lot about, but I mention it because it is one of the key industry relevant applications. Yeah, so we could think that we could apply this, like for example, privacy preserving machine learning in many different settings. So something that's often given as an example when motivating homomorphic encryption is, for example, computations relating to genomics or healthcare. So my DNA is quite personal to me. I'm quite unwilling to give it away. But nevertheless, there could be some information in my genetic data that could tell me like if I'm at risk of getting some certain disease in the future. And it could be interesting for me to know that information. I may also not want to know it, but let's suppose that I did want to know it. Then I might be willing to encrypt my genome and send it to some service that can predict this risk. But I'm definitely not willing to send my data in clear in that case. Similarly, maybe I'm already unwell and we're seeing like AI to be used to help people being diagnosed with different diseases from their scans and so on. So again, maybe it's, I don't really want my healthcare data to go to a wide audience, but maybe it'd be convenient to help me get diagnosed with something if there is something wrong with me. And then in another setting, so in finance, so here is a setting where it can be important to figure out if something like money laundering is going on or different suspicious financial activities. But obviously the banks are very private about their customers' data. So it's difficult to share information about like whether someone's doing something suspicious. Whereas perhaps homomorphic encryption, like having the data be encrypted and some information deduced about it, this could help to detect fraud or other suspicious activities in the finance setting. And again, there's also training sessions not mentioned on the slide. These are just some examples.
So just to be clear, so the idea is you would send off your healthcare data or whatever, the diagnosis would happen, and the diagnosis would come back to you encrypted without the agency doing the diagnosis.
Knowing exactly. Yeah. So it might be like you and your doctor have a discussion, you encrypt the scan, send it to a service, the service homomorphically evaluates the diagnostic evaluation, sends it back to you. Then you're the one with the key, you can decrypt it and see what the result is. But this is like quite a what if this could happen kind of thing. But yes, this could be this could nevertheless be, I think, quite valuable. Yeah, thanks for the question. Are there any other questions? Yeah.
So simply thinking, it might be kind of like unrelated, but when we think of sending information through radio waves, right? We modulate a signal with a certain frequency, some sort of wave. and then we let the receiver know the frequency of the wave. Then we demodulate it. Demodulate the wave, right? Like think of radio. Someone uses a, let's say like a 98 frequency wave, and we just turn the channel to a 98 hertz frequency, and then we receive the information, right?
Yeah.
And what's the difference between modulation, demodulation, and homomorphic encryption?
So I don't really know a lot about how radio works, but like I don't know if radio is encrypted. So if I could just tune into the channel, I can just receive data.
I was thinking,
But here, like
I'm
if people are witnessing like the wire between the client and the server, what they're seeing is ciphertext go past. They're not able to tune into the underlying data.
don't they like still get the keys? Like for example, think of radio wave. We know what frequency it comes through, right? So the receiver knows the frequency. So I might call that encrypted because they know only the receiver knows the exact frequency of the information, like the channel where it's coming. Then also in
I
this
don't know if
case,
frequency could be easily guessed.
So that would be sort of encoding, so just changing the data to a different representation, whereas cryptography is a matter of making it computationally feasible to sort of work out the encoding.
right. You can ask how it's encrypted, like the key for the person.
Yeah, I'm going to show a
alright.
specific example of
Sorry.
like the public key encryption of the BGP scheme later. Yeah.
Alright, thank you.
If I could just add something there. It's very, very similar to the fact, you know, if I'm transmitting something by radio, and you want somebody in the middle to be able to do some processing on the audio signal, but without knowing how to tune to that frequency. The whole point of homomorphic encryption is that it's encoded on the way out, but the person who's doing the processing doesn't do the decoding because they don't know how to do the decoding. They do the processing anyway, and then send you back the signal, and then you receive it. But working on the encoded data without decoding.
Yeah, thanks for the clarification. Thanks for the question as well. Okay, so I want to tell you a little bit more about one of the early applications, because I think this was a pretty cool piece of research. So this is in the privacy preserving machine learning space. It's actually a privacy preserving inference. And this is a paper by a team from Microsoft, and it was published in 2016. So it's already almost 10 years old. And it's one of the earlier papers that was published on an application, but they already had some success. So I think this is a really cool example. And so their setting was they were thinking about neural network inference in particular, and they were working with the MNIST data set, which is a commonly used data set which inference algorithms are tested on. And the data set is of handwritten digits, so like this kind of squiggly 6. And the idea is that the neural network can tell you that, yes, the squiggle is a 6, for example. So they were interested in evaluating this homomorphically. So what you would do is you'd write the squiggle, you would encrypt it, ready for inference. So then you would send your ciphertext encrypting the squiggle over to the server. The server then homomorphically evaluates this neural network. The output is some guess of like which digit the squiggle represents. Again, it's encrypted though, so it's encrypted digit 6, and then transmitted back and decrypted, and you see that we correctly classified the squiggle as a 6. Yeah.
Yeah, so I'm familiar with this MNIST data set. So MNIST data sets are actually handwritten digits, right?
Yeah.
It's already in its squiggle form. So I am not able to understand how that transformation between the original digit and the homomorphic like that part works, because it's already in that form. So what I'm doing?
Well, it's testing the idea of like if I encrypt like any squiggle, what will it classify? Like here on the slide I've drawn what I hope resembles a 6. So it perhaps doesn't illustrate that idea quite so well, but I could draw any squiggle and send it to this neural network and it will tell me it's one of 9, 10 digits. But yeah, thanks for the question. Yeah. Okay, so to understand how this is possible, because at first sight it's kind of like, oh, a neural network, that seems quite complicated, there seems to be many neurons. Maybe I haven't emphasized this enough, but like what we can practically do with homomorphic encryption is not so much at the moment, and it was even less 10 years ago. But still, like this neural network structure is actually quite amenable, at least in some sense, to homomorphic encryption. So how neural networks work, basically, at a very high level, is that the neurons are in layers, so think of like columns. And so say this neuron B, whatever's going on at that neuron is influenced by all the neurons in the previous layer. So here, these 3 neurons. And what happens is you first take a weighted sum of the values of these neurons, and then you pass it through some nonlinear function. And that's how you calculate what's going on at B, and then so on throughout the network. So the thing with a weighted sum is this is a linear function. It's a very low depth circuit. Homomorphic encryption can evaluate it easily. The noise doesn't grow too much. It's a very homomorphic encryption friendly type of computation. So that part is good. Now this F, this is typically something like a sigmoid ReLU function. It's nonlinear. On the face of it, it's not naturally amenable to HE. So you typically have to approximate it by a polynomial so that you can like write it down in terms of homomorphic additions and multiplications. And in the CryptoNets paper, what they did is they just took the approximation x squared, and this works. I thought that was amazing, with an accuracy of 99%. So, and of course, like things have moved on a long way since this early paper in terms of like privacy preserving inference with homomorphic encryption. But still, like the fact that x squared works, again, x squared very easy to implement, very low depth, just one multiplication.
Can you consider this why x squared is easy but ReLU is not?
Yeah, because like how would you write ReLU as a polynomial?
Well, that's essentially the LMS. Why is polynomial so important? Because ReLU just piecewise linear, right? So it feels like it should be very easy.
I think that the point is not ideal.
The point is above.
Because you want it to be like a continuous polynomial, at least approximated by. And then so to approximate it, I guess, well, you need a quite a high degree polynomial on a suitable range.
Yes, sorry to keep.
No, go ahead.
I guess the question is why you assume that the correct primitives for your homomorphic encryption are plus and times rather than some other operations which might
Max, for example.
Yeah, max, for example, which might give you different functions.
Yeah, that's a good question. It's because I think it's because the like in the schemes we know, the plain text and ciphertext have this ring structure. And so they very naturally have addition and multiplication. And then, so not only that, you have like your somewhat by that, and then they support this like bootstrapping. So it just fits the paradigm we have. Yeah.
So x squared is very nice to do as a homomorphic function, but any quadratic would be still just pretty much as nice. Did they try any other quadratics and did that get any sort of variation?
I don't know if they tried a variation. I don't remember the details. I think they were satisfied with x squared by itself, but yeah, that could be interesting. Yeah, it's true that like any quadratic would be equally convenient. The main thing is like the degree of the polynomial as well, so that's good news. If it gets too high, you get to make multiplications too much. Any other questions?
Silly question, but
No?
usually the W's are real, right? But the encryption method you use is usually multi-period.
Yeah. I'm going to come to this issue. Yeah, not a silly question. Yeah, you then have to approximate that also. Yeah, very good point. Okay, so yeah, moving on to another application. So I mentioned that private information retrieval is one protocol that you can build for homomorphic encryption. You could choose to build it in other ways as well, but nevertheless, okay. So here it's a protocol. It's still going on in this client server setting. Now the server is in possession of a large database of say n entries, and the client wants to retrieve one of those database entries. So the client and server engage in a protocol. At the end of the protocol, the client has requested the data at entry I and received that data packet that's the ith entry. But the security guarantee is that the server doesn't learn that it was the ith data point that the client wanted. So yeah, this is then private in the sense that the client is able to get the data it wants, but not reveal the index of value. And there is an obvious solution, which is pretty inefficient, that the server could just send the whole database to the client. That would certainly work, and the client could look up whichever entry it wanted once it had the whole database. But we want to exclude that kind of solution because it's inefficient, and also like presumably the data is stored on the server exactly because the client doesn't want to store all that data. So you want that the protocol in its communication cost is less than the cost of transmitting the whole data. So I mentioned this because this is an example where it's actually been implemented in practice using homomorphic encryption, and Apple has implemented it in this particular application of theirs. You can read more about it on their blog. So I think it's a pretty cool application, and it also, yeah, really illustrates an extent to which we're moving towards practicality of homomorphic encryption. We're not really necessarily fully practical. So the idea is that on your iPhone, you can detect if an incoming call is spam or not without revealing who exactly is calling you. So yeah, Apple in a server somewhere has a database of phone numbers and corresponding identities. And then when a phone receives a call, it encrypts the number. So the phone number is the index. And then it interacts with this PIR protocol. And then it's able to get the output, which is encryption of the identity, in this case, someone called Katie, so the identity of the caller. And then that gets sent back to the phone and it can be decrypted. And so you learn that Katie is calling you. It's not spam, it's Katie. That's cool. But yeah, so obviously Apple knows that you've received a call, but doesn't know which caller ID you queried. So yeah, I think that's a very nice example that's really being applied somewhere in the real world. And yeah, before we conclude the applications part, we can kind of ask ourselves how practical really is homomorphic encryption at the moment. So I'd say still it's moving towards practicality rather than being practical. There are a few examples of proofs of concepts, and I think partially homomorphic encryption, particularly homomorphic addition, is a bit further along the pipeline. So wherever partially homomorphic encryption can suffice, there have been some case studies reported about, but as it relates to SHE or SHE, it's still more so pilot projects, proof of concept, I would say. And so if you compare it with the other PETs, something like NPC or federated learning, these seem to be more along the pipeline towards practical. But still, it's interesting, and I've put some links to some more resources on this if you're interested in learning more. So yeah, different articles that summarize different case studies or different possible application areas. There's one from the ICO about data sharing, which is quite interesting, for example. So feel free to check them out if you're interested. And it's a good moment to pause for some questions about applications before we move on to maybe a slightly more mathematical flavor.
So companies aren't doing this out of goodness of their hearts, really. I mean, so this is driving people to, you know. So if you're wildly successful, we will put much more of our data in the cloud, and it will be owned by large companies, which again has all sorts of information. So how do you are fueling a particular view of how data is going to be managed for society?
Yes. Well, for me personally, I think like the fact that it's still on the towards practicality pipeline is good for me as a researcher because it gives me research to do. Yes, I like taking.
But you are producing a potentially double-edged, dual-edged technology that will have implications that people will suddenly discover and be uncomfortable with.
I think that's true and that's fair. I think, as it's speaking for myself personally, like I'm already sharing a lot of information with Google. Like I'm using Gmail for my personal email. So the data is being amassed by these large organizations irrespective of whether homomorphic encryption is practical. Is that a good thing? Maybe no. But at least this could offer some privacy in some sense for users. And I think, yeah, again, I think we are moving towards, like, for example, storing data in the cloud is a pretty routine activity. So if we could like leave it there stored, encrypted, and then process on it when we wanted to, I think that could be nice. But yeah, you're kind of, yeah, it's a good philosophical, good point. I'm interested to hear everyone else's view actually on that point. Maybe we can discuss that.
Sorry, I'm nearly finished my PhD in FHE, so I guess I've got a bit of a that's my disclosure of potential interest. But yeah, I feel like how I tend to explain it to people is that, well, these places are going to absorb your data in the sort of black hole, sucking everything in way that they do. And therefore, hopefully, having some encryption technology combined with that will allow you to at least have some protection while that's all happening. I think one of the issues with, I mean, you know, the Googles and Amazons and so on absorbing everyone's data, it is that they, you know, they do this and it's almost like it's unregulated because, you know, Google says, well, we have to have this information to be able to do the search engine. We have to have this information to be able to do ChatGPT. So like, what gives? Whereas I think hopefully some encryption technologies will offer an opportunity for, you know, the EU or some kind of regulatory body to say, well, you actually can't just do that anymore. And we now have a technology which means that you cannot just absorb the data in the way that you have been doing, and it's not fine. I mean, it's never been fine, but there's now like a valid, like hopefully there would be a valid alternative to say, well, now you have to do this instead. Because I fear we have gone too far down the pipeline of you cannot say no longer, you can't have all your data because it's already kind of to some extent happened. Yeah.
It's a good question.
That's my hot take.
Thanks for
But,
that. Yeah, I appreciate that.
But I think it's really like a, you know, it's sort of thing that keeps me up at night, and I don't know. It's very difficult and horrible.
Okay, so yeah. Oh, is there another thing to be?
Maybe the thing to be more worried about is like tiny rubbish app that takes all your data and has no regulation at all. So one of our colleagues at Royal Holloway did some amazing PhD research about the security of our period tracking apps, which especially in 2025, given what is going on in the world, I think maybe reproductive health is something we might be especially concerned about people having our data on. And a lot of these apps say that they use encryption, and they do not at all. And so I think anything, especially given some of the applications you talked about earlier about like advocating for the use of mathematics in society more widely and like considering the importance of it, I think this is a really cool way for some hopefully useful technology to get out there. And the thing is, the person who is using their period tracking app has no idea what's happening with it, and they shouldn't have to know. Like they should not have to have tons of knowledge or a PhD in cryptography to be able to work out what's happening. Yeah. Sorry, I'll get off my soapbox now. Thank you very much for listening.
Thank you for your comments. I agree with everything. Okay, so switching gears now, so moving away from applications, and I want to take some time now to kind of give a very high-level overview of a few research projects that I've been involved in, and mention to you like what is specifically the mathematics that we've needed in order to make progress on this research. So that would be interesting. So we need to introduce some characters. So I'm going to be speaking about the BGB and BFB homomorphic encryption schemes. These are two of the widely used schemes, most often used in the somewhat homomorphic encryption setting. And they have, the same parameters, the same plain text space, the same ciphertext space. So they have it's a variant of learning with errors called ring learning with errors. So they work in a particular ring. I'll define it in a second. But the parameters you need to know about are a power of 2 dimension n, a ciphertext modulus q, a plain text modulus t, and some error and secret distributions chi and f. Then the plain text ring for both these schemes is this cyclotomic ring, so defined by x to the n plus 1. So it's a power of 2 cyclotomic ring, and then the coefficients of the polynomials are z mod t in the plain text and z mod q in the ciphertext, hence the name of the moduli. And the plain text ring is just r mod t, and the ciphertext space is a pair of elements in r mod q. So something that's nice about r mod t is it's got a very rich structure. So here we can come to like Galois theory, for example, to kind of exploit this structure and get some efficiency improvements in the homomorphic encryption schemes. So this defining polynomial x to the n plus 1, modulo t, the choice of the plain text modulus, you can factor it. It will factor into L distinct polynomials of degree d. And yeah, they're all identical to one another. And depending on your choice of T, you can vary like what L and D are. So it could be like degree 1, and then you get like thousands of factors, or you could choose something smaller if you wanted to. And then we can apply Chinese remainder theorem. So we can see that our mod T is isomorphic then to L copies of, let's say, mod F1 of X, because they're all kind of like isomorphic to each other. So this gives us a way to kind of split a single plaintext element into L distinct elements. So this will enable us to encode data into L slots, and then that gets wrapped up into one ciphertext. So we're able to kind of parallelize computation. And even more than this, like you can, so we call this slots, like the different copies of on the right-hand side. And we can even map between the different slots using Galois automorphisms, basically. So this gives us, in addition to homomorphic addition, homomorphic multiplication, a homomorphic rotation function using this structure. So this is very nice. And you can exploit this in multiple ways. So in a recent work, what we did is we were considering the space where, the setting where you like have fewer slots of higher rank. And in this setting, you can compute these functions that are quite familiar maybe from algebra, so like the norm and trace functions. You can compute them directly in the plaintext slots. And we actually show how you can exploit this to improve homomorphic evaluation of polynomials. I unfortunately don't give any details, but I'll link to all the papers I'm mentioning at the end, and I'm happy to chat afterwards about anything. So. Okay, so yeah, we're then considering like, okay, we want to evaluate a degree D polynomial. This is a very normal activity in SAG applications. And if you're able to exploit the plaintext structure in this way and make use of these rotations, then we actually show that you can evaluate the degree D polynomials in log of D operations. Whereas if you were doing like a generic approach with like Patterson-Stockmeyer, you know, this would be like square root of D operation. So it's a quite significant saving. So this is applicable to any polynomial you may wish to evaluate. But we were also interested specifically in the bootstrapping for BFB. And this, as part of one of the operations that's done in the bootstrapping, you have to evaluate something called a digit extraction polynomial, which basically like evaluates the mod P, I guess mod T. And then, yeah, so we showed how you could apply this improved polynomial evaluation to speed up the digit extraction operation within bootstrapping. And then we implemented the bootstrapping and compared it to a prior implementation. And we found that it gives a 1.6 times speed up for bootstrapping compared to the best prior implementation. So yeah, this was really nice because yeah, we got to use some fun mathematics, and we also got to improve BFB bootstrapping, which is not easy to do. And it's like, yeah, but the reason that like BGB BFB bootstrapping is relatively slow. So that's why these schemes are typically used in the SHE setting, but like this kind of work can help move us also more to the FHE setting with these schemes. So we thought that was pretty cool. Okay, so yes, coming back to this issue about the weights of real numbers. So it's absolutely right that, yeah, this plaintext space, this polynomial ring R mod T, is not a natural space where data you might want to work with actually lives. And so you have to deal also with encoding. And so in this slide, I've thought like maybe the data you want to work with is integers, and you have the same kind of problem. So you firstly have to do some encoding to make this integer data go into a plain text in a convenient way, and then you like pass it through the encryption, you do some evaluation on it, eventually you get an output ciphertext, you decrypt it, you get an output plain text, and now we have to interpret the output plain text as some like output integer, so we need to do decoding as well. And I mentioned already that like decryption may fail if the noise is too high, but also decoding may fail even if decryption succeeds. So taking care of how things are encoded is also a quite important and interesting problem to consider. So yeah, in a work in 2018, we were again considering the BFB scheme, and we were interested in how encoding might be improved for BFB. And so the main idea of this work was, okay, instead of letting T be an integer for the plaintext modulus, what about if we let it be a small polynomial? What about if we let it be x minus b for like, let's say b equals 2? Then if you do some algebra, you can convince yourself that that makes the plaintext space directly isomorphic to Z mod B to the n plus 1 of Z. And like, okay, so B, yeah, let's say 2, n is something in the thousands or possibly 10,000s. So B to the n is a very big space. So taking the plaintext space in this way, or like kind of modifying BFB in this way, it gives you a number of advantages, which we explored. So firstly, is then very natural to encode integers, because the kind of the space directly is encoding integers. Like it's, you know, this B to the n is quite large, so you're not really going to wrap. So you can basically consider that you're working with integers. And actually, it's even more than that. It's like it's large enough that we're able to do a high precision computation in BFB, which prior to this was not really possible, and we were kind of, yeah, stuck with like kind of low precision, like medium sizes of t, like 2 to the 6 or something quite normal, for example. And so we showed that this enables you to either do faster computation or do deeper computation for the same size parameters. So by parameters here, I mean like we take the same n and q as we might do for regular BFB, and then whereas that parameter set might have supported only depth 2 before, now it can have depth 10. So this is giving, yeah, quite nice improvement. And so this variant of BFB is now known as the CRPS scheme. Okay, so I've already introduced noise to you, so I don't know if I need to restate this slide because I think I've said all these points before. But basically, as a reminder, the ciphertexts, they all have some kind of inherent noise. It's small at the start, but it grows, especially with multiplication. If it's ever too big, decryption fails, so that's not good. And so we need to understand how noise is growing throughout the computation. So either it can tell us when we need to bootstrap, or it can tell us like how big we need to set our parameters overall so that the noise in the output ciphertext is not too big, and so we're able to decrypt. And this, it's important that we set parameters large enough so that the noise, you know, so the decryption doesn't fail, the noise isn't too big. But then on the other hand, if we set parameters large, this is exactly one of the main factors that's making HE so slow. So yeah, like the ends, like I say, is in like the 10,000s, or yeah, maybe thousands. Q again is like could be hundreds of bits. So these like ciphertexts that are like size 2n1q, they're really big compared to like operating on plaintext. So we want to make parameters as small as possible for performance reasons. Okay, so I promised I'd explain to you how encryption works. Okay, so here is how encryption and decryption look like in the BGB scheme. So as for the key generation, so you might be able to see that this is giving you an LWE sample. It's actually giving you a ring LWE sample, but if you think of like writing ring multiplication as a vector matrix, you can unpack this to see this looking like the learning with errors that I presented on an earlier slide. So yeah, we're going to take a ring LWE secret to be the secret key of our scheme, and then we're going to make a public key by giving a ring LWE sample associated with it. So we choose a random ring element A, we multiply A by S, and we add some error. We scale the error by the plaintext modulus. This will be important to make decryption work. And then we send to you A and like minus AS plus T times E as the public key. Then to use this in encryption, so remember the plaintext space is R mod T, so we're encrypting an element M in R mod T with the public key that I just defined. And here, what we're essentially doing, it might be hard to see at first glance, but we're basically taking another like ephemeral ring LWE instance and using it to mask the message. So we take an ephemeral secret U and some more ring LWE errors E1 and E2, and then we like make a ring LWE sample with U and E1 and the first part of the public key, and we create that, and then we add the message to it. And then on the C1 part of the ciphertext, we then make with the same secret a ring LWE sample with the other part of the public key. So yeah, I don't give more detail than this, but you can convince yourself that this then is secure from LWE. It's hard, hopefully, at least intuitively. And then, okay, let's suppose we had a ciphertext, so this 2-element thing, C0, C1, how would you decrypt? Well, you take your secret key, you multiply it by the C1 part, and you add the C0 part. Then you take that thing mod Q, and then you interpret that thing mod T. And so, yeah, so in a line of work, we've been interested in understanding how noise behaves in the BGB and BFB schemes and similar schemes, also the CKKS scheme. So this repeats the information on the previous slide as a reminder what the public key and encryption looks like. And so we can consider decrypting a fresh ciphertext to understand like what is is the noise in like the output of encryption of fresh ciphertext. And so if you start the decryption process, so you take your C1, times it by S, add C0, and start, that's the first step of the decryption operation, and then you like write down some algebra, and you substitute in the values that you know the public key are, etc. Then after you get some nice cancelling of the ASU and AUS, you get that your output is some multiple of Q plus the message plus T times these terms that are like made up of this, the ring LWE secrets and the ring LWE errors. And I should have said that we then take these, the distributions that these are chosen from to be somewhat small, so that this term multiplied by T is somewhat small, because this is exactly the noise. And so the idea is, I hope you can then see from this, that if this T times some stuff term is not too big, then when you take the C0 to C1s mod Q and then mod T, you'll recover M as you want to, so decryption will be correct. But if the noise is really big, then maybe you get failure at the mod Q part, and then whatever you interpret in mod T is incorrect. So yeah, so we were analyzing like the noise not only in fresh ciphertext but in other operations, and we're trying to see like what can we say about it, how does it grow, how does it behave, what does it look like. And for a fresh ciphertext, it's quite nice. So for a fixed secret, the noise is normally distributed with some particular variance. So that's good. And one can think like, oh, maybe the noise could be normally distributed throughout the computation. Spoiler alert, it will not be. But we could still think it and hope that it might be. I'll tell you about some hoping we did. Erin will know. Okay, so let's think now about homomorphic multiplication. Okay, so here we want to multiply two ciphertexts. How does this actually look like in BGB? So we've got two ciphertexts. They're both these two-element things, called them C0, C1, D0, D1. Let's say the first one is encrypting some message M1 with noise V1. The second one is encrypting some message M2 with noise V2. And then how does the multiplication operation work? Well, you actually get this kind of three-element thing, which I denote here C0, C1, C2, that encrypts the product of the messages, mod T, with some noise V0. And so by the end of the slide, we're going to hopefully say something about V0. So firstly, a bit more detail on what this looks like. So this comes maybe back to the question about like, why are we so interested in like addition multiplications? So because of like this ring structure of the ciphertext space, the multiplication to produce this like three-element object is just polynomial multiplication. So like the C0 part of the object is like the C0 parts of the ciphertext, and like the cross terms is the middle term C1, and then the C1 part is the C1 D1. And this, I won't call it a ciphertext because it now has three elements. So we then need to do some more operations to make it back into a two-element thing, but I don't tell you about those operations right now. I just tell you that this object, if you also have the square as a secret key, you can decrypt it, as long as the noise isn't too big. And kind of by construction of it being a polynomial multiplication, actually this decryption equation is equal just to the product of the decryption equations of the input ciphertexts. And so what that means is that the product VMUL of the noise, right, sorry, what that means is VMUL is the product of the input noises only. So now if we want to analyze VMUL, we have to think like, what is this product of noises going to behave like? And so yeah, it's polynomial multiplication. Remember, we're working mod x3n plus 1. So the coefficients of this VMUL polynomial are going to be a sum of n terms, where each of the terms is like a coefficient from V1 and a coefficient from V2. So making some assumptions, which are quite heavy assumptions. This might give us the suggestion that something like a central limit type argument might help us to understand this object. It's going to need some heavy assumptions, right? It wants that these V1i, V2j's to be like IID for it to really hold, and n to be large enough. Well, the good news is I think n is large enough in practice for statisticians to be happy, but the independence assumption we may come across on. But still, we basically thought like maybe we can try to have a central limit type analysis and have the output from VMUL be normal, because we already know the fresh ciphertext is normal, and maybe if everything's normal throughout, this will make things simpler. But like alarm bells should already be ringing, because Like if you think about multiplying the product of like, yeah, two fresh ciphertexts when we know the noises are normal, we kind of know that the product of two normals isn't normal, it does have heavier tails. So still we might want to think, can we approximate it as normal? Okay, so we did a lot of work in this direction to try to follow this intuition of like maybe we could approximate things as normals and this will be convenient. So we did arrive at the following theorem. So we're thinking about polynomial products mod x to the n plus 1, so kind of motivated by the form of BGB noise. So like let's say the input noise is distributed as one normal and a second input noise is distributed as another normal. Then thinking about the polynomial product, we can say that its components can be approximated under some assumptions via a central limit argument as also a normal with some specific variance that depends on the parameter n and also the input variances. so that's that. Yeah. So we were like, okay, so we can at least approximate it as a normal, at least at the first multiplication. So then we kind of evaluated like, would this be better than previous approaches we know about modeling noise with BGB, which typically consisted on bounding the noise at every operation, which would be always true, but like would be kind of loose. So you possibly choose parameters that are much bigger than you actually need. So we did find after implementing this and evaluating it that this approach can give a more close modeling of the noise. And it can then enable you to choose parameters that are more performant because like it kind of tells you need parameters that are somewhat smaller than the other approach. However, there's a really big drawback. It sometimes underestimates the noise. So we've come across where we've made one too many assumptions. And obviously if we underestimate the noise, this is really, really bad because then we might let parameters go out into the wild that decryption is going to fail on. So in the end, this is kind of a negative result, but I think it was still an interesting study, and yeah, so I want to mention it also because it's like maybe you think stats is not important as you did when I was an undergraduate. I'm sorry, stats is coming back to you.
Can I just ask so I make sure I understand? So yeah. You say theorem, so you prove that because usually when you have products, you would expect some not a normal distribution, as you said earlier.
Yes, yeah, I'm suppressing a lot of assumptions in this.
And so you say you can prove that there is something that's then normal. But then you say it can underestimate the noise. So what do you mean by that?
Yeah, so I'm proving it's normal, but I haven't like listed all the assumptions, which includes like we analyze the covariance properly, but then we say like some parts of the off diagonal are small compared to the on diagonal.
So this is
and then we know there are specific cases where that isn't true also. So
okay, so your theorem is subject to certain assumptions that are usually not satisfied in practice. Is that
pretty much? Yeah, yeah, yeah. So we're kind of exploring like, can we make everything look normal? Okay. Evidence suggests we cannot.
Yeah, and I mean, you know, the financial crash happened because everyone thought, you know, everything has fast decaying tails, and they don't.
Indeed, they do not.
So there's a lot of exciting stuff here that's not normal.
The problem is it then becomes way harder to analyze. So yes, and it's even worse, right? So like, if we get to this first round, we can maybe say under some assumptions that in some cases, maybe like we've taken two fresh hypertexts, had them multiplied, looked at the noise, and that noise is approximately normal. But then we can't even keep going because this is a statement about like really things that are actually normal. So, and it turns out that like the more you multiply, the more the tails catch up with you, and it's like less and less normal. So this, unfortunately, this idea doesn't work, but it was very fun, I think. Well,
has someone made it work? Is this the state of the art, or?
So as it relates to like what's called average case noise analysis, I think this basically is still the state of the art. There's like some critiques kind of saying this doesn't work, and we even said it ourselves in the previous work. But for some schemes, this approach does work basically because like an operation called modular switching, which I haven't really explained, but it helps to kind of get away from that 3-element thing and like get things back to a normal cybertext you can keep working with. That's in some implementations, it seems to reset the noise. So then things basically look like fresh again. And then, yeah, in another family of schemes called CGGI, there they have like some, at least experimental evidence that suggests the noise after bootstrapping looks normal. And so in their setting, they're also like they bootstrap after every operation. So again, you get this kind of resetting thing.
Yeah, I think this is like completely true. I would say in a lot of practical applications, what people do is sort of put a test ciphertext, like a little sort of sacrificial rat, through the maze and see what happens to its noise in order to check that everything works. And then this means you can experimentally verify the parameters that you choose. This feels kind of horrible because it's not like a nice result as to why it happens. The other option is some people have developed some kind of formulas, which like if you plug it all into the formula, then this seems to hold. But everything that I believe so far that I've seen at least is experimentally verified rather than proved. So yeah, we are in the world of physics perhaps, and we might want to leave that for the future.
So I think it would be nice to get like, yeah, more provable results on this, but I think they're going to be like horribly complicated to analyze. So a nice question for someone to take up maybe. Okay. And I want to conclude by just mentioning our latest work led by my PhD student Alan Turing. So I hope I've convinced you that the BGB family of schemes has an interesting mathematical structure, and such structure has permitted us to make various advancements in research. And so we think there's still much more to do. And so we've developed this new Rust library targeted at FHE researchers, which implements the BGB family of schemes and is designed to expose the underlying mathematical structure in a convenient way, as opposed to different existing homomorphic libraries that are maybe also targeted towards the application developer audience, where it's more like they want to remove the structure from the user and have them implement applications. We want to like give the structure and like have people like really play with the scheme some more and perhaps make some further developments. So please check that out if you're interested. And I'll just offer a quick comparison with other major libraries that also implement BGB. And you can see that, for example, we also implement CLPX, which is nice. We're one of the few libraries that supports bootstrapping of BGB-like schemes, at least public implementations of the bootstrapping. We also support general cyclotomics, not just the power of 2n setting that I've focused on during this talk. So yeah, every paper that I've mentioned is available on the ePrint server if you want to read more. I didn't realize Daniel was going to do a plug of the book, so I've also got a plug of the book. You know, are you an aspiring cryptographer, or maybe you're a cryptographer who struggles to explain to other people what this really means? Perhaps you'd like, or are you module leading an introductory course in cryptography? I think I've covered all the customer base. Maybe you'd like to check out the second edition of a very short introduction to cryptography, which was published earlier this year. And thank you, and I'm happy to take more questions.
Are there any questions? So I'd just like to ask, we mentioned a bit about the post-quantum community, who've got this thing where they have a superstitious rejection of ring learning with errors, and sort of say, we're worried that this beautiful mathematical structure might lead to some cryptographic vulnerability in some way that we just don't understand. And so you have Frodo that says, completely do away with rings, or module learning with errors is a sort of happy medium that we've picked. That's not going to work in your case because you do want the ring structure so that you do have both the addition and multiplication. But the other sort of allergic reaction sort of said, maybe it's the cyclotomic structure. And so people have introduced things like n-true prime. Do you lose much of your sort of usability and functionality if you start moving to non-cyclotomic rings?
That's a good question. I don't know if a lot of people have explored this. I think most researchers focused on ring LWE. I've seen a bit of exploration towards even modular LWE based FHE. We've also been looking at ring LWR based FHE. And I think there've been a couple of papers that like look on this like lattice isomorphism problem type assumption and see like how homomorphic connections work in that setting. So maybe that was a partial answer to the question.
No further questions? Let's thank the speaker again.